So am I audible to all of you?
Yes, sir.
Yes,
Okay, last class, where did you stop? Can someone tell me the topic? Where did I stop in the last class? Can someone tell me where did I stop in the last class? So no one studied or what?
wait, sir, checking.
हाँ हाँ चेक करो करो करके बोलो ना. Please tell me.
There is strain.
We have, sir,
Yeah.
we have done shear strain and do some, numericals. That's it.
Numericals किसका numericals क्या?
We have
Strain का numericals क्या ना?
shear strain का भी किया. हाँ.
ठीक है ठीक है.
And we have able to see some new type of numericals in our examination also.
हाँ क्या new type क्या new type है? What new types? Tell me. All the questions are done in the exam.
Sir.
In the class. Huh? The questions are a bit twisted because in direct questions you will be not getting na. You are fourth sem now. We will give you direct questions.
With that reason, we see it as a new. Okay then.
जो सॉल्व नहीं कर पाते हो मुझे बोलो ना अगर प्रॉब्लम है.
बाद में बोलेगा, अभी देख लेगा और एक बार.
हाँ बाद में बोलो क्या प्रॉब्लम है. तुम अगर समझ में नहीं आया तो मैं समझा दूंगा ना. लेकिन एग्जाम में तो डायरेक्ट क्वेश्चंस नहीं आएगा ना. समझा?
Yes, sir.
Fine, sir.
सॉल्व किया कि नहीं तुम लोगों ने? क्वेश्चन सॉल्व किया कि नहीं तुम लोगों ने? Can you see my screen?
No, sir.
So let's discuss Hooke's law. So what is Hooke's law actually? When stress is directly proportional to strain, then we get what? Hooke's law. Okay. Now, the stress is directly proportional to strain. This is also called as Young's modulus. Okay. So this is also known as Young's modulus. So first of all, this is the Hooke's law. According to Hooke's law, the stress is directly proportional to strain. Okay, and the coefficient E. That means what? When stress, this is sigma and epsilon. If you see here, so this is sigma and this is E. Now this epsilon, these two are what? Directly proportional. So if these two are directly proportional, then we'll have one constant, which is known as what? E, or modulus of elasticity, or Young's modulus. Okay. Then similarly, we have bulk modulus and shear modulus. Now, if you see here in Hooke's law, the stress is directly proportional to strain, then this, what do you call it, this proportional limit, that is Young's modulus, it comes into play. Okay. Now this is limit is known as the, yeah, who's there? Please mute yourself. Please mute yourself. This is known as Young's modulus. Now, in volumetric strain, look.
Sir, I can't see the screen, sir.
Yeah, I'm just giving the lectures. The screen is not shared yet. I'm just giving the lectures. Just try to listen to it. So, in case of volumetric strain, there are stresses that will vary as per the volume. Now, if it varies as per the volume, then what will happen? Then, like we saw, it is change in length per unit length in one case, right? So, if it is change in length per unit length, then there will be what? Change in volume per unit volume. So, we'll have to find out there the volumetric strain. Okay, so these are the different cases. Can you see my PDF?
No, sir.
Okay, I'll share this PDF with you people also. Okay, now if you see here, the modulus of elasticity just now we discussed. Now modulus of rigidity or shear modulus. This modulus of rigidity or shear modulus means ratio of shear stress to the corresponding shear strain. This is known as what? Modulus of rigidity. Okay. Now, there is a relationship between the stress and strain. Now, the stress and strain relationship is given by what? It is given by Hooke's law. Now, just remember this one. In Hooke's law, it states that when a material is loaded with elastic limit, the normal, this is the particular statement of the Hooke's law, okay? When a material is loaded with elastic limit, the normal stress is developed is proportional to the strain. That means stress is directly proportional to the strain. This is the basic principle of Hooke's law. Now look, there is in one dimensional strain, only strain is in only one direction, but in two dimensional strain, the strain will be in two different directions. Okay, now look, for two dimensional stress system, we will have one is what, longitudinal strain, and the other is what, lateral strain. The longitudinal strain is what, when a body is subjected to axial tensile load. Now if the body is subjected to axial tensile load, then we call it what, longitudinal strain. So this is what is called longitudinal strain. And then lateral strain, the strain that is coming at the right angles, this is known as the lateral strain. Okay, so these are the two differences between longitudinal and lateral strain. Now we go to another important topic, that is Poisson's ratio. Now look, okay, I'm giving one another example for lateral strain. For lateral strain, what is happening is the pull is happening from this side, if you can see, and then this breadth will decrease, right? But the length will increase. Okay, so this is how the lateral strain is occurring. Now Poisson's ratio. Poisson's ratio is what, the ratio of lateral strain to longitudinal strain. And remember one thing, Poisson's ratio is different for different materials. Okay, the ratio of lateral strain to longitudinal strain is known as Poisson's ratio and is different for different material. Now this is an important topic. Analysis of bars of varying cross section. Now look, I hope all of you can see the PDF. I hope all of you can see the PDF.
Yes, sir.
Yes, sir.
Yes?
Yes, sir.
Okay. So look, here this is a bar of varying cross section. Now if you see here, the pull is applied P, but the cross section is A1, A2 and A3. The bar is what? Varying, and the length is also L1, L2 and L3. Okay, now the load subjected to it is P. P is the pull or the load that is being subjected to it. Now, for here, the P is the axial load that is acting on the bar for this particular case. L1 is the length of section 1. A1 is the cross sectional area of section 1. L2, A2, L2, A2 is the length of the cross sectional of the area 2. And L3 and A3 is for 3. For this age. Now, E is what? The Young's modulus of the bar. Young's modulus means, just now we discussed, the stress strain ratio is constant. And that proportionality constant is Young's modulus. Now, if you see here, then you can see that the stress for section 1, first of all, you have to find the individual stresses for section 1. That means P by A1. Why P by A1? P is the load applied, A is the area. That is why load per unit area is P by A1. Then similarly for stress for section 2 and 3 is P by A2 and P by A3. Because the same load will be applied in A1, A2 and A3. So that is why force per unit area. Okay. So this is how we compute. Now strain in section 1. That means how will you find out strain in section 1? Now look, I'm giving you this one. If you see, sigma is the stress and sigma is proportional to what? E,
Strain.
right? Yes or no? Good, very good. Then we'll have that constant, na? So you can put this equal sign, then we get this E equal to small e. That means what? Stress, which is this, divided by strain is Young's modulus. So we can write it like this: E1 equal to sigma 1 by E, because sigma 1 by E1 equal to E. You can write like this. Yes or no? Yes or no?
Yes, sir.
कोई respond करो बेटा.
The Young modulus will same for all section.
हाँ, देखो, Young's modulus is a property of a material. Now we have assumed this bar to be of same material. Are you getting me what I am saying?
Okay, okay.
हाँ,
Okay,
एक
okay.
सेम मटेरियल का होगा तो सेम होगा, समझा? अगर if it is a different material, then it will be different. But you getting my point? Are you getting my point? Hello.
Yes,
So okay, good. So we can write like this: sigma 1 by E. Then sigma 1 we know P by A1. Then we can write like this: P1 P by A1 E. Yes or no? Then if you go to the next part, similarly for section 2 and section 3. For section 2 and section 3, we have E2, epsilon 2 and epsilon 3. So the change in length per original length. This is given by epsilon 1. Now look, E2 and E3 we obtain like this from here before. Now what will happen? This E1 means what? Strain in 1, right? Strain in 1 can be written like this, dl1 by l1, where dl1 is the change in length of section 1 and l1 is the total length of the section 1. Huh? Similarly, we can write for others also. Then we can write like this now. This dl1 is equal to E into l1, which is the change in length. So change in length dl1 equal to EL1 equal to this one PL1 by A1. You can write, because E1 equal to P by A again we know. Here we just found out for E2 P by A2E. So E1 equal to P by A1E, then E2 equal to P by A2E, and E3 equal to P by A3. That means what? Total change in length of the bar can be found out by adding all the DL. All the DL if we add it, then we'll have to put these values, this one, and this one here, and then we found out this. So this is the basically equation and formula for finding out the length, change in length of a bar of varying cross section. I hope this is clear. I hope this is clear for everyone.
Yes, sir.
Anyone having any doubt? Bar of varying cross section and all. Anyone having any doubt?
Clear, sir. Clear. It's clear.
Clear है? ठीक है. Now to for clearer concepts, I will show you a video. Wait, give me a minute. Let it pass. Now, if you see here in this bar of varying cross section, you might get numericals also. I'll show you one example of this. Now, this is the question. Wait, I'll take a screenshot and can you see this question? Can you see one's question here?
Yes,
Yes,
sir.
sir.
So
Yes, sir.
why don't you try to solve it now? Or you
Okay.
can take a screenshot of it also. Have you taken the screenshot of the question? This type of questions might come. This type of questions you have to solve it like the pattern. I hope this is clear for everyone. Have you taken the screenshot of the numerical?
Yes, sir.
Can you try to solve it? Just try to solve it out using that formula just now I gave. Let's show you a video for clearing the concept of Poisson's ratio. Can you see my screen? Can you all see my screen?
Yes, sir.
Yes, sir.
No.
Yes or no?
About how different materials
Yes, sir.
are loading.
Yes, sir.
Let's get right into it. We can start with a quick example. The rubber band. If you take a rubber band and stretch it along its length will obviously increase, but it is also quite intuitive that at the same time, the band will get thinner. Poisson's ratio can tell us how much thinner the band is going to get. What about for a generic lump of material? Take this little orange cube. If we apply a compressive force to it, it will expand in the directions which are perpendicular to the direction in which we are applying the load. We call the direction along which the load is applied the longitudinal direction, and we call the perpendicular directions the lateral directions. If we reverse the direction of the force to apply a tensile load, the cuboid will obviously extend in the longitudinal direction, and it will contract in the lateral directions. The key concept here is that when you apply a load to a material in one direction, the material will also deform in the lateral directions. Poisson's ratio is the parameter that tells us how much the material will deform in the lateral directions. To define Poisson's ratio more precisely, let's take a closer look at the case where a tensile force is applied. First, let's give names to the various parameters involved. Lx, Ly, and Lz are the original dimensions of our cuboid along the x, y, and z axes. Delta Lx, delta Ly, and delta Lz are the changes in these dimensions after the load has been applied. They are shown as being divided by 2 because the change in dimension occurs on both sides of the object. Next, we can write out the strains in all 3 directions. As a quick reminder, strain is a measure of deformation and is defined as the change in length divided by the original length. It is denoted using the Greek letter epsilon and is usually expressed as a percentage. When we apply our longitudinal load, it turns out that the resulting strains in the lateral directions are equal. And here is the interesting part. They are proportional to the strain in the longitudinal direction. The ratio between the longitudinal strain and the lateral strain is actually a material constant. You might have guessed it by now, but we denote this material constant with the Greek letter nu, and we call it Poisson's ratio. By the way, Poisson's ratio is named after this guy, Simeon Denis Poisson, the famous French mathematician who formally defined the ratio in a note published in 1827. You might be wondering why a minus sign slipped into the equation. Remember that by convention, tensile strains are positive and compressive strains are negative. The minus sign is just there so that for the typical case where the lateral strains are opposite in sign to the longitudinal strains, we get a positive Poisson's ratio. Now is probably a good time to mention that this equation and the concepts described in this video only apply for isotropic materials, which are materials which have the same properties in all directions. We are also assuming that the materials are deforming within the elastic region. Things get a bit more complicated when plastic deformation is involved. Anyway, to summarize, Poisson's ratio is a dimensionless material property which tells us how much a given material will contract in the lateral directions when we pull on it in a longitudinal direction. Now that we know what Poisson's ratio is, we can look at some typical values for different materials. Without getting too deep into the math behind it, it's useful to know that the theoretical range of possible values for Poisson's ratio goes from -1 to 0.5. In practice, most real materials have a Poisson's ratio of somewhere between 0 and 0.5. Most metals have a Poisson's ratio of around 0.3. Here are some typical values for a few selected materials. Now let's look at how different values of Poisson's ratio affect how a material deforms under loading. We'll keep things simple and consider a two-dimensional case. Most materials have Poisson's ratios between 0 and 0.5. When a tensile force is applied, these materials contract in lateral directions, as we have already seen with our orange cuboid. Materials with a Poisson's ratio of 0 are interesting. When a longitudinal tensile force is applied, there is no deformation in the lateral directions. One material that behaves in this way is cork, which has Poisson's ratio close to 0. This property makes it a very useful material for certain applications. A great example is the cork in a bottle of wine. Because it doesn't expand laterally when compressed, as you can see here, it can easily be inserted into the neck of a bottle. A material with a larger Poisson's ratio would be much more difficult to insert, as it would expand in the lateral directions when compressed. Finally, we have materials with negative Poisson's ratios. These are known as auxetic materials. They expand laterally when pulled, and contract laterally when compressed, which seems counterintuitive. These are mostly engineered materials, like special foams, rather than materials occurring naturally in nature. This animation should give you an idea of how it is possible to get negative Poisson's ratios. You can see that as the material is compressed, both its longitudinal and lateral dimensions are reduced. For a typical material with a Poisson's ratio larger than 0, you would expect the lateral dimensions to increase when the material is compressed. Because it tells us how a material deforms, Poisson's ratio is a very important parameter in continuum mechanics for determining how a body responds to applied stresses. Let's look at a simple case of uniaxial stress, the tensile test. It is easy enough to determine the strains acting on a small piece of the specimen under test. The applied stress is a normal stress in the x direction, sigma x. The strain in the longitudinal x direction is simply given by Hooke's law as sigma x divided by the Young's modulus E. Even though there are no stresses acting in the lateral y and z directions, there will be strains in these directions as the material is contracting laterally. The strains in the lateral directions are obtained by multiplying the longitudinal strain by Poisson's ratio. This is just using the definition of Poisson's ratio, which we covered earlier. But what if we look at a more complex case, where we have triaxial stress, with different stresses in all three directions? In this case, we can't just use Hooke's law to determine the strain in the x direction, because it will also be affected by the strains in the y and z directions. The simple version of Hooke's law for uniaxial stress no longer applies, because the strains in one direction will depend on the stresses applied in all three directions. We can use Hooke's law in combination with the equation for Poisson's ratio and the principle of superposition to obtain the equation for strain in the x direction. We can rearrange this equation into a more practical form, like so, and then apply the same process to obtain equations for strains in the y and z directions. These equations form what is known as the generalized Hooke's law and can be used to determine deformations for a case of triaxial stress. There is one last case I would like to mention, which is materials with a Poisson's ratio of 0.5, the maximum value in the theoretical range we discussed earlier in the video. Let's return to our cuboid to introduce the concept of volumetric strain. Volumetric strain is a measure of the change in volume of an object under load. I'm sure it will come as no surprise that it is closely linked to Poisson's ratio. We can calculate the volumetric strain by summing the strains in all three directions. Let's use the equations from the generalized Hooke's law we just covered to expand the equation for volumetric strain. We can then rearrange the terms to end up with the following equation. You might notice that something interesting happens to the volumetric strain when Poisson's ratio is equal to 0.5. We end up with a volumetric strain equal to 0. This means that for materials with a Poisson's ratio of 0.5, the volume of the material remains constant as it deforms. These are known as incompressible materials. Rubber is an example of an incompressible material. And that's it. We've reached the end of our review of Poisson's ratio.
I hope the concept of Poisson's ratio is now clear for everyone. Anyone? Can anyone respond?
Sir.
I hope the video is clear. Concept is clear.
Yes, sir.
Okay.
Sir,
बोलो
hello.
बोलो
हाँ सर, हेलो सर, अभी का जो न्यूमेरिकल पूछना था थोड़ा,
कौन सा न्यूमेरिकल?
जो अभी आप दिया था ना सर,
हाँ हाँ बोलो बोलो.
इसमें सर जो लेंथ का जो डायमेंशन जो सेंटीमीटर में दिया हुआ है ना, यूनिट जो सेंटीमीटर में दिया हुआ है, एंड देन यंग मॉड्यूलस यूनिट इज गिवन इन द न्यूटन मिलीमीटर स्क्वायर. सो डू वी नीड टू कन्वर्ट दिस?
तुम बोलो तो कन्वर्ट करना पड़ेगा कि नहीं पहले? What according to you?
So according to me, it should to match
should
the
what?
units. It
should
should
what?
convert. We should convert it to match
Yeah,
the
good.
unit, you know.
Very good. Convert it. ठीक है? Convert करके solve करना. समझा?
And then sir इसका
हाँ.
जो एरिया का जो दिया हुआ है ना, the area that given, इसका जो हाइट दिया हुआ है 3 सेंटीमीटर 2 सेंटीमीटर, ये लास्ट में क्या है? DIA डायमीटर लिखा है क्या?
हाँ, डाया है, डायमीटर. डायमीटर से तो
ओके.
सेक्शन एरिया निकल पाएगा ना.
हाँ ओके.
पाई स्क्वायर बाय 4 है कि नहीं? समझा?
So with the help of this diameter we can find the area na sir?
Yeah.
Okay.
Okay, good.